So now we are going to learn about different methods for making a statistical decision. So the first one in this case is your rejection region approach. In the rejection region approach, the first step is to check the conditions which are necessary to run the test, and you will then set the hypothesis for that particular test. Now, next you will decide the level of significance alpha. The value of test statistic will be computed depending upon whatever setup you had, right? Whether sigma is known or it is unknown for mean, or maybe in case of variance, what will be the test statistic, or finally in the case of proportion also. So we will see in different cases how your test statistic varies. So that basically incorporates the idea of the sampling distribution that we have been studying so far. Next, we are going to find the appropriate critical values for the test, and you will write down the critical region or the rejection region for the problem. Finally, you will see if the test statistic falls in the rejection region, you would reject the null hypothesis, and if it does not fall in the rejection region, you would fail to reject the null hypothesis. So these are the common steps that are adopted in the rejection region approach. Next one, that is your p-value approach. In the p-value approach, the first three steps are exactly the same. So basically it means that you will check the conditions and then you will set the hypothesis, decide the level of significance, okay? And so all these basically, and calculating your test statistics. So that would be the same in this also. Now the moment when you enter the fourth step in the previous case, where you have to calculate the rejection region and you have to compare it with the critical value. So in this case, we would find out the p-value. So let us see what it is. So you would find the appropriate critical value based upon the alternative hypothesis. Okay. So here, if the p-value that you have computed is less than your alpha, then you would reject the null hypothesis, and if it is not less than alpha, then you fail to reject the null hypothesis. And finally, you will conclude in your own words whatever you have observed. Okay, so this is the basic, or you can say the background of both of these approaches. So we will see more in detail now. So the first case here would be the test about one mean, because if you know, we will be working on two mean problems or the two sample problems in the next week. So right now we are going to focus on situations where you have a single population and you are taking a sample from that, and you are interested to estimate, or you want to check the claims, whether whatever the claims have been made about the population parameter are correct or not, based upon the single sample only. So the first criteria that we have been looking in all these problems is about the mean. So whenever we talk about mean, we have two situations. So here you can see that in the normal distribution, normal mu sigma square, when I'm interested in this mean, sigma square has two options. This can be known or it can be unknown, right? Because when it is known, the test statistic would be different than when it is unknown. Okay, so if you can recall from the sampling distribution chapter, so we have found there that if it is known, then you will have your standard normal distribution coming into picture. But in this case, when it is unknown, your t distribution would come. So we will see how the test statistic gets modified here. So first thing that we are going to look at, the case is when sigma is known. Now, when sigma is known, you have the first case as the right tail test. Note that any hypothesis testing, when you are dealing with the hypothesis testing, you can either have a two-tailed test, right? A two-tailed hypothesis test, or a one-tailed. When we say one-tailed means that it can be either right or it can be left-tailed. So here, when we say right-tailed test, so basically it aligns with your alternative hypothesis that you are looking at values which are greater than something, right? Or greater than the threshold values. So there we say that it is right-tailed. Likewise, in the left-tailed, it will be just the reverse. So there the alternative would be in the way that we are just interested to see whether the population parameter is less than the hypothesized value or not. Whereas in the two-tailed, as the name itself suggests, we are going to look at both the directions. So we are not just focusing on whether mu or the population mean would be greater than the threshold value or the hypothesized value, or it will be less than. So we are just saying that it won't be same as mu naught. It can go in either direction. So that is the two-tailed. So now let us first focus on this one. So we are talking about your one-tailed test, that is your right-tailed in this case. Now, to understand this, let us consider a very simple example. Suppose a person makes a claim that the average height of Indian women is around 150 centimeter, suppose. Now you want to test whether the claim that has been made is correct or not. And you want to frame it in the right-tailed test. So here, what is your 150? 150 is basically the hypothesized mean under the null hypothesis which is given to you. So this is the value mu naught which is already there, and now we want to verify whether the average or on an average or in the population does it actually hold or not. Is the average height of Indian women greater than 150? So you believe somebody has made this claim and you want to verify it whether it is less than 150 or not. So in this case, you will frame your null, which is just the remaining half, that would be mu less than equal to mu naught. To test this, what you will do is you will write the test statistic first of all. Okay. So the test statistic would be in this case, because it is this case of sigma where it is known to you. We know that here in this case x bar follows normal with mean mu and variance sigma square by n, and then we said that okay, so if I have x bar minus mu sigma by root n, this would follow normal, standard normal distribution. So that this is basically your z star. That is the test statistic that you have calculated. And your null hypothesis, suppose if we consider this one, null hypothesis based upon your example would be mu greater than 150. So your interest is in this alternative one and you want to reject the claim that is your null. So the next step would be you would reject the null hypothesis if z star is greater than equal to z alpha. Z alpha is basically the critical value that you will find from the table, and z star is the test statistic that you have calculated just now. So now if you consider it in this way, so somewhat here, this is your z alpha and this area is basically alpha. Now it is saying, or maybe I could use the capital Z alpha, also it is fine. We can keep it. So we would be rejecting the null hypothesis if the test statistic that you have calculated over here is greater than this, or basically it is falling to the right of this line. So you would be rejecting the null hypothesis in that case, because it is now aligning with your alternative. It is greater than z alpha, or the critical value that is there. So this would be your rejection region approach basically. And in the p-value approach, you would calculate the p-value. So basically p-value is the probability that you would observe a more extreme statistic than we did if the null hypothesis was true. Now here, probability that z greater than this is basically, what is this? This is the probability of this is basically your standard normal, right? This is your random variable. So we are finding the probability that given the null hypothesis true, what is the probability that this z is going to be greater than your test statistic? Or you could say that given the null hypothesis is true, it means that this condition is true, that is H naught mu less than equal to 150. If this condition is actually true, that the average height of Indian women is less than 150 centimeter, then you have to find out the probability that you would observe a more extreme statistic than you have observed, that is Z star greater than equal to, it means we are looking at Z star and greater than that. So you would observe a more extreme statistic than what you have already observed given the null hypothesis is true. So now if this probability is small, here if you check that whether it is less than alpha, if the p-value that you have found is less than alpha, it suggests that extreme result is unlikely to occur under the null hypothesis. And then you would reject the null hypothesis. So what is happening over here is, we are saying that if the null hypothesis is true, it means actually if the population has the average height of average Indian women have basically height less than 150, if this is actually true, then this probability that you would observe a more extreme statistic, this should not be very, very small, because you have observed, you have taken the sample and you have observed the p-value, you have obtained the answer to that. Now, if this is not holding true, if you are getting a very small p-value, this probability is coming very, very less, it shows that under the null hypothesis, this is not going to happen. So it means that it is happening under the alternative, in fact. So that is why here also we reject the null hypothesis if p-value is less than alpha. So you just align it with the definition, whatever you have studied for the p-value, and then you can understand this point over here. Okay, so in both the approaches that we have written over here, we are first of all writing the null hypothesis. You would check the conditions, obviously. You will write the test statistics. So here you see that till this point, both the approaches are same. And then it depends whether it is a rejection region approach. So you will find the Z alpha. And if it is a p-value approach, then basically you would find this p-value. Next is your left tail test. In the left tail test, here you can think of it from this point of view, that the alternative says that we are focusing on those observations which are less than mu naught. So in this case, so it would be something like this. So you would have minus Z alpha here, and it is alpha this side. So this side you will reject the null hypothesis. If you just consider from the previous concept, previous slide that you have studied so far. So you have framed your null and alternative in this way. Okay. So whatever, just keep in mind that whatever the name of the test is, that comes basically in the form of the alternative. Okay, it does not have anything to do with the null. In fact, it is aligned with the alternative, that mu is less than mu naught. Okay, because we are talking about the left tail test. When it is right tail, it means we are talking about those values which are greater than something. So that is why we will have the right tail test. So now also we will have the test statistic. So you see that test statistic is same, because in these cases we have assumed that sigma is known to us. Now you would be rejecting if your test basically if the test statistic that you have calculated, and you will find your Z alpha, if it less than minus Z alpha, then what you will do is you would reject the null hypothesis. So here basically negative sign here indicates that we are dealing with values that are less than the mean, and which basically aligns with your alternative. Because here if you have this, we are talking about minus Z alpha, right? So you have got certain value which is falling, Z star is a negative value in this case. So here you would have something alpha over here. So if Z star basically if it is falling in this region, you would be rejecting the null hypothesis. Okay. What will happen in the p-value approach? Same thing. P-value is again the probability that you would observe a more extreme statistic. So in this case, extreme can be on the left side also, right? So probability that z is less than equal to z star. And here also we would reject the null hypothesis if your p-value that you have calculated comes out less than alpha. So just to keep, if you want to keep some things in mind, whenever we have left-tailed, so that whatever left or right, so it will be aligned with your alternative over here. Now one more thing you should note here, that this test statistic that you calculate over here is basically calculated under the null hypothesis, right? Because that is why you have mu naught, equality sign is in the null hypothesis, and that is why you have, under the null hypothesis, you have calculated the z star value, and in the you want to reject it based upon that only. So here also you see z star is coming. So z star is that value which was calculated under the null hypothesis, which means that basically assuming that null hypothesis was true. But still, if the null hypothesis is true and your p-value comes out to be very small, which is less than alpha in fact, so then you would say that it is unlikely to happen under the null hypothesis. In fact, it would occur under the alternative hypothesis. Okay. And if you note here that when we say left tail, so left tail, we are talking alternative is in this side. It is in the same way. We are talking mu naught, mu less than mu naught. Then also if you see this value over here, reject h naught if z star is less than equal to minus z alpha. Again, you are looking at, if you see the sign basically here is same as your alternative one. Again, z star is less than, you are talking about the left tailed. Same thing would come in the p-value also, because in p-value also we are looking at the probability that z is less than equal to z star. So this is just a basic thing that you can just to keep in mind. Obviously, if you are getting confused, then you should think about from the point of alternative hypothesis. Okay. Now finally, you will have two-tail. Two-tail means that it can go in either direction. It can be either less than mu naught or it can be greater than mu naught. So when alternative is two-tailed, then your null would be basically that it is same, it is taking mu naught only, right? So if somebody is claiming that, okay, the average height is not 150, so your mu naught is 150 in this case. So the null hypothesis in this case would be mu equal to 150 against the alternative that mu is not equal to 150, right? So it all depends upon what problem you are tackling, right? Either you want to check that the average height is more than 150, then you would go with the right tail. If you want to see that no, average height is less than 150, then your left tail would come. And or in the last case can be, you want to see that no, it is not 150, it can be either less than or greater than, that does not matter, but it will not be exactly 150. So in that case, you would have the two-tail test. Again, your z star would be the sample mean minus mu naught over sigma by root n, right? Because it is calculated under the null hypothesis. Because when I say x bar follows normal with mean mu variance sigma square by n, so it is under the null hypothesis, so it is in fact mu naught over here. So then you will have x bar minus mu naught sigma by root n under the, it will follow standard normal. Now you would reject the null hypothesis if the value that you have calculated, that is this test statistic, is greater than equal to z alpha by 2. So basically it shows that here, because it is two-tailed, it will have these two, and the total alpha, that is rejection region, would be divided into alpha by 2 because it is symmetric, alpha by 2, and in between would be 1 minus alpha. Okay. So you can see that it can lie on both the sides, right? So rejection would happen if mod of this value here is greater than equal to z alpha by 2. Sorry, it will not be z alpha, it would be, sorry, it would be z alpha by 2 and z alpha by 2. So it is coming because alternative you have mu not equal to mu naught. It means it can go in either direction. So that is why your test statistic also could fall in either way, right? It can be less than minus z alpha by 2 and it can be greater than z alpha by 2. So that is why it can be written as that mod of z star is greater than equal to z alpha by 2, right? Likewise, your p-value would be twice of the probability that z is greater than equal to this absolute value of z star. Now, why do we have this twice, basically 2 written over here? This 2. So this basically accounts for extremes in both the directions, right? Because the extreme values can happen in the left tail also, in the right tail also, okay? Because it is a two-tailed test. So in this case, we have this 2 coming into picture and we check this probability that z is greater than equal to mod of z star. So if you are adopting the rejection region approach, you would compare it with the critical value, and if it is the p-value approach, you would find this probability that z is greater than equal to z star, that you can find easily from any standard normal table, or if you are using any software, then from there also you can easily find out. So we will learn all those things. And finally, you would reject if the p-value comes out to be less than alpha. Now here, if you note that in these 3 tests, we have been looking at rejection region and the p-value approach both. Now if you think, so rejection region was an older method and nowadays we work more with the p-value approach. The reason being is that obviously here if you see, once you have calculated the p-value, right? Now if I fix alpha at 0.05, I can easily see, okay, alpha is less than 0.05, or if somebody takes, no, I will take alpha 0.01. So it can be immediately verified. You don't have to calculate the p-value again and again. Once you have calculated it, that is done, right? Unlike here in the rejection region approach, because if I change alpha every time, this z alpha valued by 2, this critical value will also be updated, and then you would have to compare it with this value, the test statistic, whether it is satisfying this criteria or not. So that is why it is basically not straightforward, and every time you update alpha, your critical value is getting updated, and then you have to compare it. So you are adding more steps to it. Otherwise, if you look just at the p-value, it is simple, because once you have calculated the value, that is it. You will just now simply see, okay, it is less than alpha or not. So that, and obviously it is easier to interpret also, because we are talking in terms of the probability that something is happening or not. So that basically makes our conclusions and interpretations easier. So that is why p-value is more used in nowadays. So let us look at the example over here. Suppose a smartphone manufacturing company wishes to determine if their products typically last longer than 40 months. It's assumed that the lifespan of these smartphones follows a normal distribution, and historically the standard deviation has been around 15 months. To investigate this, the company selects a sample of 50 smartphones and records their lifespans, and the sample reveals that an average lifespan is of 45 months. So now you have to check whether there is significant evidence to support the claim that the average smartphone lifespan exceeds 40 months or not, right? So you have to find support for that, and you have to take alpha as 0.05. So that is already given to you. So here what is happening? What you are given is typically lasts longer than 40 months. This value is given, and then standard deviation over here is given. Okay, you will have 50, so it means it is about the samples n, that is sample is n over here. Average lifespan, it means it would be x bar for you, right? 15 months of standard deviation, this is sigma, because it is for the population. So it means we are talking about the situation where the standard deviation is known to you, and this is basically your mu naught over here. So mu naught over here is 40 months. You have to frame your null and alternative depending upon this. So let us see how do we solve this. First thing is that you can use the one mean z test over here that we have seen just now, because you have, first of all, the sample size, if you see, that is 50. Obviously it is greater than 30, so you could apply that test. And also because your standard deviation is known to you. So okay, so one z test would come in here. And now when you are trying to set up the hypothesis, the alternative would be that the average lifespan is actually greater than 40, and rejection of, or basically the null hypothesis would be that it is less than 40. Because if you see over here, you are saying that a smartphone manufacturing company wishes to determine if their product typically lasts longer than 40 months. So it means here they are interested to see if it is greater than 40, right? So you can write the null hypothesis as that, okay, no, the lifespan is going to be less than 40 months. So that is how you can get the hypothesis over here. Now you will, the second step is to write the alpha value that is given to you as 0.05. You will calculate the value of the test statistic. So x bar is 45, 40, right, is this mu naught over here. Sigma is 15 and you divide by root 50. This basically comes out around 2.357. So you can see here that I have written x bar just to show that, okay, instead of capital X bar, that was a random variable. And here, since we have the actual value of those sample observations, I have calculated the sample mean. So basically it is 45. Okay. Now if you look at the z alpha, so z alpha would be, alpha is 0.05. So if you look from the standard normal table, this z alpha comes out as 1.645. So because it is a right tail test, so you will reject the null hypothesis as if your z star is greater than equal to your z alpha, right? Because your null over here, if you see, it is mu greater than 40. Okay, so you would be rejecting the null hypothesis if the z value, that the z star that you have calculated, is greater than equal to the critical value. The z star is 2.357. Okay, and so 2.357, you have to compare this with 1.645. So we can know that this is greater than that, right? So since the value of the test statistic falls in the rejection region, so rejection region is basically those values z star which is greater than 1.645. So you reject the null hypothesis. When you reject the null hypothesis, this indicates that there is sufficient evidence to support the claim that the average lifetime of these smartphones is greater than 40 months at 0.05 significance levels. Okay, so you're rejecting the null hypothesis and you are accepting the alternative that, okay, mu is greater than 40, that the average lifespan is actually greater than 40 months. So this is how you can easily do your hypothesis testing using your rejection region approach here. Now if you have the p-value approach, as you know, the first three steps would be same, because you have set the hypothesis, you have the alpha value, and you have the test statistic value also. So what you have to do is, now you have to now find out the p-value. Now p-value in the right tail test is basically probability that z is greater than equal to z star. That is a test statistic. That is a probability that you would observe a more extreme statistic than we did if the null hypothesis was true. So z star is basically calculated under the null hypothesis. So this value was 2.357, and if you look at the standard normal table, you will find that it actually comes out as 0.009212, right? Now you can easily compare this with the alpha value. Alpha is 0.05. Obviously, so you are going to reject the null hypothesis and conclude that you have sufficient evidence from the data that the average lifetime of the smartphones is greater than 40 months. Okay, so now here in the last step, if somebody tells you that, okay, no, this is not, alpha is 0.01 or anything else, then you can easily compare it. right? Unlike the rejection region approach. Okay, so this was about the one mean test when we were trying to find out for the situation then standard deviation is known to you. Okay, the second case can be when the standard deviation is unknown. Likewise, here also we will have the three situations. So we will look at the left-tailed, right-tailed, and you will have the two-tailed. Now the difference over here would come when you are dealing with the test statistic, right? Because when sigma is known, in all the three cases it would be same. The test statistic would be same because you know that sample mean would follow normal distribution. And in this case, when it is unknown, if you can recall that we will be using your t statistic or your t distribution, sorry. So here, the right tail test, it is in the same way that mu is greater than mu naught. Okay. Your test statistic would be what? It would be denoted by t star because just to keep alignment with the t distribution, so we are using t star here. So here if you see x bar minus mu naught, and here you will have the sample standard deviation. So whenever sigma is unknown, we estimate it using your sample standard deviation, and whenever we do that, so if it is under the null hypothesis, if you replace this sigma by root sigma by s, then basically it no longer follows your normal distribution, but in fact it follows t distribution with the degrees of freedom n minus 1. Right? So you would calculate the t star now. Note that again, this is calculated under the null hypothesis because under the null hypothesis we have mu equal to mu naught here, right? So that is why mu naught is coming. You're not writing mu. Keep this in mind. You don't know mu basically, and you are interested to find out. You want to extract the information about mu. That is the average mean, right? Or you can consider that same height examples. You are interested in the average height of Indian women, and that is mu. That is not known to you. But what you know is your mu naught. Whatever the claim that somebody has made, that is the given value to you, or the hypothesized mean value that is given to you. So the test statistic would be calculated once you know those values, right? Obviously under mu naught, that is under the null hypothesis, because samples mean you would know, right? This value would be given. Sample standard deviation would be known to you, n would be known. So obviously here, if this is known only, then only you can find out. So it is calculated under the null hypothesis. Rest of the things would remain the same because here you would reject the null hypothesis if t star is basically greater than t alpha. So you calculate the test statistic if it is falling in the rejection region or the critical region. So here you will have your t alpha if it is falling in this region. So basically you would say that you would reject the null hypothesis, right? Because it is in this way. Okay. The value that you are having is greater than the critical value. So we reject the null hypothesis and accept the alternative. Again, if you have to find the p-value, so p-value again, same thing. Even when you're writing z or t star, that won't matter. The concept of the p-value remains same. So basically, given the null hypothesis is true, you are finding the probability that you would observe a more extreme statistic than what you have obtained now, right? And if the p-value comes out less than alpha, so you would basically suggest that extreme result is unlikely to occur under the null hypothesis. Okay, so instead of that z, it is replaced by t in this case, right? And z star, you would have your t star. Okay, so you would reject because probability that t is greater than equal to t star. Note this, this and this. Okay, so again left tail would be mu less than mu naught because we are dealing with the left tail of the distribution. T star again under the null hypothesis or test statistic would remain same in all the three cases. you would reject the null hypothesis if T star is less than minus T alpha, because we are dealing with this side basically. So minus T alpha is here, you would have your alpha values on this side, right? So minus over here basically shows that we are dealing with those values which are less than the mean of the distribution, which are less than mu naught. That is why you are getting a negative sign with the T star, right? And this basically aligns with your alternative, that population mean is actually less than the hypothesized population mean. And p-value, obviously again you are focusing on the left tail, so it would be probability that t value would be less than your test statistic. So you look at this particular probability, and if it comes out to be less than alpha, you would reject the null hypothesis. Okay. Likewise, you can have the two-tailed. Again, it can be either less than or greater than. The test statistic would remain the same. And now the same situation will happen, because here you have these values. So here you have minus T alpha by 2, and this side you will have T alpha by 2. So again, the total area alpha is divided, because it is symmetric, it is equal on both the sides, and in between you will have 1 minus alpha, because the total area under the curve would be 1. Okay. So you would reject the null hypothesis if it is falling in either this region or in this region. So it can be written as this. Likewise, p-value. Again, here also you are taking twice of it, because the extreme values can occur on both the tails, right? On both the ends. So that is why we have this, we multiplied by 2. Obviously, in left and right tail, we do not multiply it by 2. The reason is this only, because we have to deal here in two-tail test, we have to deal with the extreme observations on both the sides. Okay. And finally, we would reject the null hypothesis if the p-value is less than alpha. Now let us look at an example. Imagine that a Hyundai Motor Company is curious about the average fuel efficiency of their cars, with the company's manager asserting that a car should have an average of 25 km per liter. Assuming that the mileage follows a normal distribution, the company decides to verify the claim. To do so, they examine 40 of their vehicles, so sample size is given to you, and find that the average fuel efficiency is 28 km per liter, and the standard deviation across these vehicles is 10 km per liter. At alpha as 0.01, determine if there is enough statistical evidence to conclude that the average mileage is different from the manager's claim. Okay, so this value that is given to you, that is your mu naught. Now sample size is given to you as n over here. This is your x bar, and this is your sample standard deviation s. You have to check whether the average mileage is different. So different means that it can go in either direction. Okay, it is not left tail or right tail. In fact, it would be a two-tail test in this case. So how do you identify that which test you have to apply here? Either the sigma is known or unknown thing, right? Z test or the T test over here. Because in this case, your sigma is unknown, and that for that you have from the standard deviation is given to you across these, that is 10 km per liter. So you could take it as basically that the condition is satisfied, right? So for the rejection region approach, you would set up this basically. Null hypothesis and alternative would be this. Your alpha value is 0.01. You will compute the test statistic basically. So here this is 28 is given to you, 25 is this value, mu naught s by root n, and you get 1.8973. Now if you look at this value, this would be 2.023. So from the table you will find that t at 0.005, because it will be t alpha by 2. Okay, so alpha is 0.01 in this case, right? Yeah, since alpha is 0.01, you would see that this value over here is 2.023. So the critical value is this. So the rejection region would be T star either on this side or on the right tail test, right? So either side here in this way, either this portion or this portion. So this is basically minus 2.023 and this is 2.023. So if the test statistic is falling in this region or this side, you would say that you would reject the null hypothesis. And what actually you have is that the value that you found here is 1.8973. So since the value does not fall in the rejection region, you fail to reject the null hypothesis here. And hence, you will conclude that you do not have enough statistical evidence to reject the manager's claim that the average mileage of the cars is 25 km per liter. Okay, so obviously whatever you conclude at the end is actually equally important, because you cannot just find the test statistic and you have found, okay, we are going to reject the null hypothesis. Obviously you have to interpret it in your own words, because when you are working with any company or if you are working with a client, so they would be interested in what is the final conclusion, right? And that interpretation has to be your job. Okay. Similarly, the p-value approach, the first three steps would remain the same. And since it is a two-tailed test, you would find the probability as twice of this. And if you look, this is approximately 0.0326. Okay. You can look at the t-table. And finally, since this p-value is less than alpha, you fail to, it is greater than alpha here, so you fail to reject the null hypothesis. Okay, so here these values you can easily find using your softwares. Okay, so in this example, suppose a physician is exploring the effectiveness of a novel diagnostic method, and the established method yields an average recovery period of 10 days. That is the old method. It's assumed that the recovery duration using the new method follows roughly a normal distribution. To assess this new approach, the physician observes the recovery times for 10 different patients and records their durations in the number of days as follows. Now, the physician intends to conduct a statistical test with a significance level of 0.01 to determine if the new diagnostic technique significantly reduces the average recovery time compared to the conventional method. Okay, so here the data set is given to you, unlike in the previous examples where you were given the sample mean or the sample standard deviation. So here actually you have the data set. Obviously this is just for 10 patients. Likewise, you can have a bigger data set, and from there for those values you can calculate the sample mean, you can calculate the standard deviation. Once you have calculated those values, then you can come back again and use this method to solve the testing problem. So the rejection region approach here would be, you will use the one mean t-test, obviously, because you do not know about the population standard deviation. So z-test won't be used here. And the research hypothesis would be that mu is less than 10. So the alternative is that the time is actually less than, so if technique reduces the average recovery time, right? So older method took 10 days. So now we are interested to see whether it is taking less than 10 or not. Alpha is 0.01 and this test statistic again. So this basically shows that when you have this data set, X bar comes out as 9.5, S comes out as 1.58, N is obviously 10 in this case, and mu naught is given to you as 10, which is over here. If you solve this, this basically comes out as minus 1.0007. So test statistic is there. Now you would calculate your critical region. So for that, if you look at the table, so you will find that this actually is 2.821. So T alpha. So alpha here is 0.01. Okay. Since alpha is 0.01, sorry, this would be, just cross check this value, I think it would be t 0.01. okay, because alpha, because it is left tailed only, so either this is a typo error or if this is the actual value, minus 2.821. okay, so considering that here it is the correct value, minus 2.821, so your rejection region would be whenever t star, that is a test statistic, is less than. Now your test statistic is actually minus 1, right? So it is greater than your minus 2.82, so you fail to reject the null hypothesis again. Since you do not have enough statistical evidence to conclude that the average recovery time using the new technique is less than the recovery time using the old technique. Okay, so you fail to reject it, it means that it is not actually less than 10, that is your alternative. So the p-value approach over here, it will follow the first three same steps. We will compute the p-value, so t would be less than, this is the test statistic that you have, and you look at this value, it comes out as 0.177. So even if you are looking at the t table for the given alpha and for the given degrees of freedom, because here we are dealing with 10 observations, so degrees of freedom would be 9, right? So for alpha as 0.01 and degrees of freedom 9, you can go up, you can find in that table for the right tail test in the t table, you can find out that this probability is actually 0.171. You can actually read it from the table, but the t table may not be that exhaustive as compared to your standard normal distribution table. So you can instead use the software that we are using, Python or maybe anything else that you are comfortable in. Now since this p-value is larger than alpha, again because alpha is 0.01, we fail to reject the null hypothesis. Okay, thus we will conclude that we do not have enough statistical evidence to conclude that the average recovery time using the new method is going to be less than the recovery time using the old technique. Okay, so what we have seen till now is that we have considered the two methods of hypothesis testing. So one is the rejection region approach and the other one is the p-value approach, and we have looked at the test for the single mean, and since there would be two situations, so the first one being your when sigma is known, then the test statistic would vary, while when it is unknown, then the test statistic would be something different, that in terms of t distribution it would come. Also we have seen that how the one-tailed, two-tailed, or you can say the right tail and left tail, all these three tests basically vary. What is the difference between them and how do we approach such problems? So this was about the mean.